All right, so this starts the endocrine system. So just a quick overview, we're going to go over the endocrine system. The hypothalamus will be the control center of the endocrine system. The hypothalamus will act on the pituitary, which is going to be the master gland. And I want to know that the hypothalamus produces two hormones of its own, ADH, anti-diuretic hormone, which works on the convoluted or the collecting duct, because the antidiuretic hormone actually creates holes to create water to come out of the collecting duct and save the water. And oxytocin is for contraction during labor. So oxytocin is actually one of the only positive regulated hormones. So the pituitary is the master gland, as I said earlier. The thyroid will be with a lot of the metabolism, T3, T4. And calcitonin. Calcitonin will be used to tone down the amount of calcium in the body. Parathyroid will be the calcium, the parathyroid hormone. Adrenal glands, you'll have the cortex, which will make the steroids, which are nonpolar hormones. These are cortisol and aldosterone. The all and own suffixes are going to tell you that these are non-polar. The adrenal medulla will make the catecholamines, epinephrine and norepinephrine. Gonads will make the sex hormones, and pancreas will be used to regulate blood sugar, insulin, glucagon, and somatostatin. Insulin is the beta cells, and glucagon is the alpha cells. So just to kind of go over some of the terms in endocrine system, you've got the autocrine, which are basically it's going to be self-regulating. Paracrine, which will be regional, so somewhere like close around. Juxtacrine is actually right next to each other, and endocrine is at far distances. So let's start with the endocrine system. So the endocrine system is when you have direct hormones in the bloodstream, and these are distant locations. The types of chemical signaling are paracrine, which are communications between near cells. Para is side by side. That's the Greek term for side by side. Juxtacrine is cell to cell communication between close or contacting cells. Juxtacrine is very close, whereas adjacent is more paracrine. Like these are all nerve cells, because you have the synaptic cleft, because you'll have the cleft in between, but the juxtacrine is actually when they're touching and they're very close. Autocrine is releasing hormones and the cell talks to itself. Signals to the cell may make signals to release to itself to essentially tell it to start reproducing and dividing. Hormones and cell membranes. So hydrophilic is not hydrophilic means polar, likes water. Charged particles like water. So peptides, there's a lot of charged proteins. These are going to be the hydrophilic hormones, which have cell receptors, because the hydrophilic can't go through the hydrophobic cell membrane, whereas the hydrophobic hormones are nonpolar and will be able to pass through the cell membranes, both the nuclear membrane as well as the outer membrane. So the steroids can cross, therefore they don't really need a secondary messenger and can directly regulate transcription. Something I want to note is these peptide hormones right here. They have extracellular receptors. They're fast and short acting because they act on an already created protein, and they allosterically, they can affect it by changing its shape or, increase its activity. For example, if you have something that's going to create a lot of CAMP will act on another molecule which will phosphorylate other things. So for example, CAMP may act on like protein kinase A, which will cause a kinase cascade. The positive feedback, before I go into that, peptide hormones are usually with the in suffixes. So oxytocin is an example. Oxytocin, like I said earlier, is one of the only positive feedback hormones. And there's very few positive feedbacks because it's very hard to regulate the positive feedback loops. So the peptide bonding will cause secondary messengers such as CAMP, like I said earlier. And the mnemonic that I want to say for peptide hormones is, it's insane how many peptides end with in. So insulin, oxytocin, prolactin, vasopressin, somatostatin, and then there's ACTH, and glucagon. These are the two exceptions. But these are the peptide hormones, and a lot of them are going to end with in because it's proteins. Whereas you have steroid hormones, which will end in -one, -ol, and -oid. These have to cross plasma membrane and regulate transcription. So these are slower, more maybe permanent. They're slower because they have to regulate the transcription, and then the protein will be translated, or the gene mRNA will be translated, and then obviously made into a protein. Steroid hormones, because they are hydrophobic, will need to have proteins that carry them in the blood because they do not dissolve in the blood like the hydrophilic peptide hormones do. And some of these carrier proteins are albumin or globulin. And there's a lot of aromatic chains in these steroid hormones. So the mnemonic for these is, well, there's a lot of them ending in -one, -ol, -one, -ol, oids. So testosterone, estradiol, aldosterone, cholesterol, glucocorticoids. Amino acid hormones. So these are less common, and you'll see them ending with an "ine," and INE, so ine. So epinephrine, norepinephrine, thyroxine, and the T3. You've got the structure is going to be small peptides. So unlike the actual peptide hormones, these are basically about like 1 to 2 to 3 amino acids. They act either as steroid hormones or the peptide hormones, depending on the structure. So if it's got a lot of aromatic rings, it's probably going to need a non-carrier protein because it's a non-polar hormone. And the reason it's non-polar is because, well, the resonance, you might have, some polar, quote unquote, polar groups, but the resonance in the rings will distribute the negative charge. And this is a summary for the peptide and steroid hormones. So for the peptide hormones, they're going to be made by amino acids. They will be polar and impermeable to the membrane, and therefore they can be dissolved in the plasma membrane. I shouldn't say protein. The receptors for peptides are in the membrane. They use a secondary messenger since they can't cross the membrane. They're quick acting and they last for short terms. And examples are insulin and ADH, and also ACTH and glucagon. Whereas the steroids are made by cholesterol. This is why a lot of them are nonpolar, because cholesterol is a lipid. Nonpolar, therefore they're permeable to the membrane. They need carriers such as albumin, intracellular effect at the nucleus. They will turn on transcription inside the nucleus, and they're slow and need to make proteins. These usually last a little bit longer, and examples of steroids are testosterone and estrogen. So let's talk about negative feedback loops. So negative feedback loops are really great because what they do is essentially your end product will be able to come back and turn this off. So this loop right here, you might have a little positives that will, eventually get to the final product, but the final product is coming back and turning something off, then it's going to be a negative feedback loop. So aldosterone, so let's talk about the low blood pressure loop. So aldosterone will be created when you have low blood pressure. So low blood pressure will increase activity of angiotensin 1, and then from renin it's activated, and then it's turned to angiotensin 2, and ACE inhibitors will be working on to stop the angiotensin 2. From angiotensin 2 you will get aldosterone, and the effect of aldosterone is that it increases the sodium reabsorption in the distal convoluted tubule to increase the blood pressure, and the final result is that it shuts off the beginning of the pathway. And positive feedback loops, on the other hand, are very hard to regulate. And an example of a positive feedback loop is oxytocin. And the final result will increase the stimulus. It's shut off by birth. So what I want to do is the anterior pituitary hormones are flat peg. Flat are the tropic hormones, FSH, LH, ACTH, and TSH. These will cause other hormones to be released. Whereas the direct hormones, prolactin and endorphins, are going to they're going to be directly acting. Section 2, we're going to talk about the actual endocrine glands and the hormones. So, like I said before, this is primarily negative feedback, self-regulation, and the only positive feedback is the oxytocin. So the first one I want to talk about is maintaining plasma osmolarity and volume. So before we look at this graph right here, what I want to focus on is that ADH lowers the osmolarity and aldosterone will increase the blood pressure. And in the hypothalamus, you'll have a portal system which is going to the anterior pituitary, whereas the posterior pituitary, there's actually just a neuron that's going to the synapse. So in antidiuretic hormone, it's a peptide hormone, and aldosterone is a steroid hormone. Antidiuretic hormone, ADH, is going to be released by the anterior pituitary, going back to that flat peg. Um, it'll be released by anterior pituitary. And this is released in response to an increase of blood osmolarity. So the idea of ADH is that it wants to decrease the blood osmolarity because the blood is just too concentrated. So when the body realizes it's got too much blood osmolarity, it'll increase the H2O which leaves in the collecting duct, and therefore it'll decrease the osmolarity by diluting the blood. This will increase the blood volume, obviously, because you're adding more water to the circulating blood. Whereas aldosterone, on the other hand, is a steroid cholesterol hormone, which is produced by the adrenal cortex. This is going to be released in response to lower blood pressure, which is also lower blood volume. This increases the sodium-potassium pump activity in the nephron, and therefore it'll increase the blood volume and the pressure, because as it pumps Na plus out, some of the water will leave with it too. Blood glucose regulation, glucagon, insulin, and somatostatin. You really don't need to know much about somatostatin. The MCAT will only test you on glucagon and insulin. The glucagon are produced by the alpha cells, which increase the glucose concentration in the blood by release. So, for example, glycogenolysis will release glucose from the breakdown. And fatty acid beta oxidation will also increase the glucose because the glycerol can go back up to glucose through gluconeogenesis. Insulin, on the other hand, decreases the amount of glucose in the body and used for storage. So this is fatty acid synthesis, glycolysis from decreasing the glucose, and glycogen synthesis. And as you can kind of see this trend of A, B, D, GIS. This is kind of alphabetical if there's a way to remember it. Diabetes, so type 1 is the autoimmune disease where your beta islets are destroyed by the autoimmune system. And type 2 is obesity linked where you have unresponsive insulin receptors. And you'll have, if there's unresponsive insulin receptors, your body won't use up the insulin, or you won't use up the glucose, so your levels of glucose will always be rising and cause some issues there. Other hormones which affect the glucose, so you've got cortisol, which is produced by the adrenal cortex, and this is stimulated by the ACTH, because ACTH is one of our flat peg, it's one of our flat tropic hormones. This will enhance gluconeogenesis and stops insulin action. So cortisol will be used to create glucose and stop using up the glucose. Epinephrine will be stimulated by the sympathetic nervous system. This causes glycogenolysis and fatty acid release by the adipose tissue so that there's more glucose readily available for the flight or fight response in epinephrine. And epinephrine is above the kidney, so this is the adrenal medulla, whereas the adrenal cortex is the cortisol. So cortisol is cortex. And thyroxine is thyroid gland, which is stimulated by thyroid stimulating hormone. This is that T part of the tropic. And one of the positives is that glycogenolysis and sugar absorption of the thyroxine gland. This is where a lot of the metabolism T3, T4 is produced too. So calcium controlled by the thyroid and parathyroid. So these are antagonistic. The thyroid will decrease the calcium by releasing calcitonin because it tones down the amount of calcium in the blood. The reason this works is that osteoblasts will build up the bone by using up the calcium, and this increases bone formation, kind of as I said with the osteoblast, and decreases GI tract absorption of calcium, whereas the parathyroid will increase the calcium readily available using the parathyroid hormone, and this increases calcium absorption in the bones and reduces the calcium excretion from the kidney because the osteoclast will cleave the bone and release calcium. Vitamin D will help with reabsorbing calcium from the gut. And to go back to our flat peg, anterior pituitary hormones are FSH, luteinizing hormone, ACTH, and TSH, thyroid stimulating hormone. And insulin is actually released by the pancreas. So there's a problem which is talked about if you had a tumor at the pituitary, which of the following will be not affected. And insulin is by pancreas, so it's not even near the nervous system. So pick insulin for that. Hypothalamic pituitary gonadal axis. So the sexual development in females, this is how it kind of works. So the hypothalamus will release GnRH, and the hormone from the hypothalamus will act on the pituitary master gland, which will release FSH, follicle stimulating hormone, and LH, luteinizing hormone. Follicle stimulating hormone will produce estrogen, which is for development and reproduction. Estrogen establishes the uterine wall, whereas the luteinizing hormone will work on progesterone, which is uterus for fertility. This stops the corpus luteum from rupturing, and progesterone protects the wall. So in a little diagram right here, we've got GnRH at the hypothalamus, which will act on the follicle stimulating hormone at the anterior pituitary, and then that will work on estrogen, which establishes the wall, and then LH from the anterior pituitary will work on progesterone to protect the wall. So FELP, if you want to remember FSH acting on estrogen. And the menstrual cycle is broken up into two phases. You've got 0 to 14 days, which is the follicular phase, and 14 to 28, which is the luteal phase. So in the follicular phase, FSH will be the first hormone that's produced at the highest. And if you kind of look right here, if you divide the follicular stage and the luteal stage, FSH directly acts on the estrogen, as I said earlier, the FELH. So as FSH increases, you'll see an increase in estrogen as well. And then you'll have the luteal stage where you see a very high spike in luteal hormone, and then the luteinizing hormone, and then that will cause a sharp rise in progesterone. So to kind of go back to it, where we're going to have the FSH and the estrogen, their functions, the estrogen will establish the uterine wall, and then progesterone will protect that wall. So that's why you got to first establish the wall, and then you got to protect it. So that's kind of how it's working. So follicular phase, rise in FSH will lead to a rise in estrogen, and then luteal phase rise in LH will lead to a rise in progesterone to protect the wall and establishing the wall as estrogen. Finally, let's get to the male reproductive system. So this is going to be working really with much more simpler than the female reproductive system, where we have FSH and luteinizing hormone. So FSH will actually stimulate spermatogenesis, and then luteinizing hormone will lead to testosterone, which is male development. And then the summary of the hormone by organs. So we've got the anterior pituitary, which will be flat to peg. And essentially the way this is going to work is that FSH will mature germ cells, luteinizing hormone will secrete androgens, ACTH will secrete corticosteroids, TSH will influence metabolism, thyroid stimulating hormone, prolactin will produce milk, endorphins inhibit pain, and growth hormone will be bone and muscle growth. Posterior pituitary is ADH and oxytocin. ADH will increase water reabsorption in the kidneys collecting duct, and posterior pituitary will also produce oxytocin, which promotes uterine contraction and milk letdown. The thyroid will produce T3, T4, calcitonin. So T3 and T4 is more metabolic rate, whereas calcitonin will decrease the calcium in the blood. And the other thing I want to know is that if you have a hypothyroid, you're probably not going to be having as much metabolism, and you're going to be really slow, cold. And then when you have too much of a thyroid working, you'll have a lot of metabolism. You'll be feeling hot all the time, because metabolism is a exothermic reaction, and breaking of glucose is exothermic, and you'll be giving off heat. And the parathyroid hormones, or PTH, will increase calcium in the blood. Adrenal glands, glucocorticoids, mineral corticoids, cortical sex hormones, and epinephrine, norepinephrine. Glucocorticoids will increase the blood glucose. Mineral corticoids will increase sodium reabsorption. Cortical sex hormones will stimulate the sex differentiation between males and females, so like testosterone and estrogen. Finally, you have pancreas, which is insulin, which is uptake and storage of glucose, and glucagon, which is a breakdown of glycogen. Finally, we're just going to have a master summary of all the endocrine hormones. So, kind of going through all of them, let's just go through them. So all of the anterior pituitary hormones are going to be water soluble. And so are basically all the pituitary hormones will be water soluble. That means they are probably peptide hormones. The ones I want to focus on are ADH is going to be water absorption by the kidney, and this will increase the blood pressure. And we've also got FSH, which will be growth of follicles in the males, growth of follicles in the females, and sperm production in the males. Now let's get to the adrenal cortex. The cortex gland hormones are going to be lipid soluble. Aldosterone will reduce Na plus secretion and increase K plus secretion, which raises the blood pressure. Cortisol will increase the blood levels of carbohydrates, proteins, and fats. The adrenal medulla, epinephrine, norepinephrine are water soluble. Thyroid, you've got the T3, T4, so those are lipid soluble, and those ones actually have a lot of rings, so they'll be lipid soluble, whereas calcitonin is a peptide, so it's water soluble. This will lower the blood calcium. Parathyroid is also water soluble and raise the blood calcium. And parathyroid work with osteoclasts, and the calcitonin works with osteoblasts. The ovaries, you got estrogen and progesterone. These are lipid soluble. Basically, all of the sex hormones are going to be lipid soluble. Estrogen will lead to the LH surge, and progesterone is for protecting the uterus. And finally, let's get with the placenta. The placenta also produces some hormones. So HCG is going to be to stimulate the corpus luteum to grow and release estrogen. Estrogen will enlarge the mother's sex organs to stimulate prolactin secretion, and progesterone will maintain the uterus for pregnancy.